Brain Banter is a podcast about the goings-on of Columbia University neuroscience professors and the stories behind who they are, how they got to where they are, and the motivations and explanations behind their research. My name is Lila Bear, and I'm your host. On the show today is Dr. John Morrison, professor of philosophy and head of the new cognitive science program at Barnard. So, one thing that we like to start off with is to kind of understand how you got to where you are and track it a little bit. So can you tell me where your interests have stemmed with philosophy and with science?
Sure, absolutely. Well, I was in high school. I went to a summer debate camp, and it was taught by a philosophy professor. And immediately I just realized this is the kind of way I like to think about the world and questions and problems. And I was kind of scandalized, though, that somebody was doing this for a living. I thought it was kind of ridiculous. It was like somebody told me they're a professional bowler. You know what I mean? It's like on the one hand, you're like, wow, that's cool. But secretly you're thinking like, wow, that's not a career. That's not something one does. And to the extent you're getting paid for it, I'm kind of wondering if society should put its resources somewhere else. But then I started to realize it's a good scam. Maybe I could do it eventually. So I knew pretty early that I wanted to go into philosophy. I've come to appreciate the value of philosophy a lot more than I did when I was a freshman in high school. Now I think it's essential and important. But yes, that's kind of how I always knew I wanted to become a philosopher. So and then the science part of it, well, my dad's a chemist, so that probably played a role. My sister was actually the first cognitive science major at Wellesley. So it was probably very much in my family culture to have a scientific focus on things. And it also just became increasingly clear to me as an undergraduate that, especially towards the end, that the questions I interested in were also at least partly scientific questions, especially since what always gripped me were questions about the mind. And I got to graduate school in one program, and it was nice, but there wasn't really a scientific focus, so I switched programs. And in philosophy, at the time, that you could know a little bit about the science and do just fine. But when I got tenure, I decided I wanted to know a lot about the science. So I got a fellowship from the Mellon Foundation to just spend a year studying neuroscience. And the Zuckerman Institute at Columbia was very kind, and they gave me a desk and were very supportive, and people were willing to meet with me. And so I've just spent the last few years learning as much as I possibly can about the relevant sciences. So particularly cognitive neuroscience, and very particularly computational cognitive neuroscience.
One thing that I want to know is what inspires your research? How do you know what to dive into?
Yeah, it's pretty broad. Well, I'm interested in the mind. So to some extent, I knew what sciences were going to be relevant. So I have friends in the philosophy of physics, and they work with physicists, and friends in philosophy of language, and they work with linguists. And I'm interested in the mind at a level of description that's above the neurons. So it has to do with cognitive functioning. So that helps narrow down the list of subfields, I guess, to focus on. Look, there's a longstanding tradition in philosophy of trying to work on conceptual foundations of different sciences. So like I said, like the philosophers and the physicists have been working closely together pre-Einstein. And you really, going back even further to people like Newton, there was no distinction between doing what we would call straight up philosophy and doing physics. So that kind of connection has been there for a really long time. Likewise, a place where philosophers work a lot with mathematicians is on logic. So logic really came out of a bunch of conversations between philosophers and mathematicians in the late 19th century and early 20th century, at least in its contemporary form. And so in a lot of universities, Columbia is actually different in this respect. There are people with joint appointments in philosophy and mathematics. Now, there hasn't been this level of collaboration between philosophy and neuroscience. And I think in part because neuroscience, with some exceptions, grew more out of biology, where there was fewer interactions with the philosophers. And another thing is that until relatively recently, neuroscience has been just not advanced enough to make real substantive claims about cognition. But that's starting to change as well. So at the present, there's some interaction between philosophers and neuroscientists, but not really the kinds of collaborations you see in the other examples that I gave. But I think it's finally at a point where those kinds of collaborations are necessary. And neuroscience is also just fun because it's at a really immature developmental point. We don't I mean, the joke is you look at the book Principles of Neuroscience, and it just gets fatter and fatter every year. But that's not principles then. That's just a whole lot of facts. And it's just intellectually the Wild West. And so as a philosopher, that's exactly where I want to be. And the amount of disagreement you see among neuroscientists about the right approach, especially to something like cognition, is just tremendous. Like they agree on almost nothing with each other. So what are some basic kinds of questions? Well, the two of them that really interest me have to do with what is a representation, and another one is what is it for the brain to compute. So if you want to think about the brain as a kind of computer, just in the sense that it's doing something sequential, automatic, and involves information about the environment, then you have to think about the brain. Well, it can be hard to figure out exactly what the relevant computations in the brain are, how you could figure them out, when the brain is representing an edge, when it's representing a shape, when it's representing a face, when it's representing some higher level abstract property of shapes. And so these kinds of questions are hard to answer just through neuroscientific methods alone. They're in a way more conceptual, and that's kind of where the philosopher enters the conversation.
So when you say representation, can we link that to just the visual system? Is that where?
That's a great example. So going back a long way, the thought is the visual system works like this. You start off with a whole lot of retinal information, which is in no way integrated. So you just have basically a bunch of, not quite, but a bunch of points like in a dot matrix, okay. And then you emerges from that some representations of lines. And then there's further operations and you get representations of two-dimensional shapes. And then you have representations of those two-dimensional shapes distributed in a three-dimensional volume. And then you get three-dimensional shapes, and then you get colors, and then you get parts and wholes. And so that's just vision is a classic example of how representations are supposed to start off simple, and then you build more complex ones. And eventually you have faces and scenes and hands belonging to bodies and stuff like that. So that's the kind of thing. But it comes up in memories too. So when you remember something, what is that? Well, it's stored information. In other words, a kind of representation. And so you can ask questions about where and how information is stored in memories. Or when you are solving a problem, say a decision problem, a navigational problem about where to go next, that too seems to involve representations, because you have to have some representation of where you are, some representation of the space around you, and then some representation of a path that takes you to where you want to go. So whenever you start thinking about the brain in these kinds of more cognitive terms, it's almost impossible to not think about it in terms of what it's representing and where.
So as a neuroscience student, I am thinking about it very neuroscientifically. How would you incorporate philosophy into representation?
Well, just this, what is a representation, and what neuroscientific evidence would convince you that you'd found a representation of an edge? So one classic way of doing this is to look at what are called receptive fields. Basically, you found a representation of an edge if it responds to edges. So you showed a bunch of a solid line. You put a solid color in front of it, it won't respond. But then all of a sudden, if you put the edge in the middle of the receptive field of that neuron, it starts to crackle. So that would be this is the kind of approach to representation that comes out of Hugel and Wiesel. So So who did the famous work on the cat striatum, where they showed them basically edges, and showed that they found neurons that were responding to them. So anyway, that's one approach you could have to what's being represented. One problem with that is that there's a bunch of problems with that, but one problem with that is that it's unclear just because a neuron responds to something, you don't necessarily want to say it's representing it. So an example of this is if you take a frog, and you can have some neuron that, say, fires off when there's something small, dark, and moving around like a fly. So in ecological terms, it makes sense to think that it has a fly detector. But you can also put lots of other things there, like BBs on strings, that will also make the neuron fire. So if you just took the approach I said earlier, where you just say, well, anything it responds to, it represents, you'll have the weird result that it just represents small dark thing. It doesn't represent flies, where ecologically, it seems this thing was designed to detect a certain kind of thing. Or, imagine like a detector for snakes in the periphery. Most of the time it goes off, there's not going to be a snake there. But nonetheless, you think the function of the role of it is to detect snakes. So just looking at what something is actually caused by might not be the best way of figuring out what it represents. So you want to look. So that's one reason to want to look at how it's used later in the organism's behavior as well. So anyways, that's representation. So that's one thing I've been working on, is what the right view of representation is or should be.
So what do you think? I'm interested.
Basically, I think the representations emerge when you compare one thing to something that came before it. So give you like the classic, take like Pavlov's dogs, which maybe I'm sure all of your listeners know what the Pavlov experiment, but for those that don't, you teach it that when you ring a bell, that you're about to bring out food, and then when it sees the food, it salivates. But if you do this combination enough, bell, food, eats, eventually it'll salivate just when it hears the bell, because it associates that with there is about to become food present. So one way to think about what it's doing is that it's saying, for each time the bell rings, it goes, oh, another one of those, which is all of the things that indicate that food's about to come. I think that kind of operation, grouping the current stimulus together with past stimuli, is the basis out of which representations are made. And this has a number of advantages. It can explain how the same neuron can represent one kind of thing for a while and then a different kind of thing later on, as the environment changes, which is one of its attractive features. So I think this view has exactly one proponent right now, which is me. So it's maybe not a guide to what the field as a whole thinks. So some people really care about why, going back to the frog and the example I gave earlier, they think that really matters is why the neuron was selected for, what purpose it was selected for. I think the obvious problem with that is it's naive to think that, first of all, it's naive to think that individual neurons were selected for. And it's also pretty unclear why what happened in evolutionary history should determine what something represents now. And another sort of general problem is that whenever you try to look at how something is used, it gets tricky, because the same, take for example, a representation of a square. Like the representation of a fly, it's clear what the evolutionary function of that would be to help you detect flies. But what's the evolutionary function of detecting squares? Well, it just serves a tremendous number of different functions. And so it's hard, there's so much diversity between all those functions that's hard to figure out to have some then prediction about what it's representing right now. Because it could be used for, gathering berries or avoiding cliffs, or, just make up your own story. And anyways, that's another whole tradition approach to representation, looking at evolution. And there's some reasons to be a little skeptical of it. So this is such a messy issue, but right. One of the issues is, what is the right size in the brain to look at? So the human weasel, they're looking at individual neurons, but we probably shouldn't think that representations are just individual neurons. They're often populations of neurons, which respond differentially to lots of different stimuli. So it can be hard to say how many and which neurons are included in a given representation. And I think this is what you're getting at, which is that it's not like these population of neuron either all goes off or is silent. So there'll be a range of stimuli, some of which are more exciting to them than others. And that can make it somewhat hard to say what it represents. The correlations are very complicated too. That's the other thing. So, so I hope you can at least see why there's these are real conceptually complicated questions, because the correlations are complicated, the things in the world are complicated, what's going on in the brain and the size of them, these are all complicated. And somehow out of all this data, all these correlations, all these interactions, you want to have a relatively simple theory about, well, what is happening right now in the brain? What is it representing? And that's a really hard thing to achieve.
Agreed. Wow. Yeah. To study philosophy, do you think about it all the time? I feel like I would just look at everything with a new perspective. Do you like carry this with you everywhere you go?
I don't know if it's any deeper than the science. I mean, so as a scientist, one probably goes around saying, well, how does all of this work? And what explains everything? And philosophers are in a way asking similar questions. So how does this work? What is the right explanation? So does it, I mean, in a way, it's a mindset. I mean, I've met some neuroscientists that are as philosophical as any philosophers that I know. So it's a kind of curiosity about what's happening around you, and a real desire to get clear about things, including things that are often the hardest to get clear about. So I think you should take a philosophy class. That's what I think.
I mean, yeah, I would love to. I read this book called Consolations of Philosophy. It really changed my life. So and then ever since then, I feel like I think about things differently. So that's kind of why I asked that. But anyway, to move on, I know you teach a class about AI and neural networks. Can you talk about that a little bit?
Yeah, so I teach this class with Christos Papadimitriou, who's a professor in the computer science department. And the basic, so for those that don't know how artificial neural networks are, these are basically these really dumb networks of sometimes hundreds of thousands or millions of nodes that you train up on some data, and that have proven to be shockingly good at learning from that data how to behave in the future. So a good example of that is they're really good at recognizing handwritten numbers. And so you give them a whole lot of handwritten numbers and you tell them what the right answer is. And through that training, they change the weightings of the connections between nodes in those networks. And it turns out they're just exceedingly good at saying when someone's written a 1 or a 2 or a 5. So likewise, all the software you see that says, and Facebook or whatever says, in this photo, is this my friend Betty Sue? That's all neural networks, because if you give them enough data, they're extraordinarily good at learning how to extrapolate from it to future data. So especially in visual tasks. So recognizing handwritten digits, recognizing faces, recognizing cats or dogs, or people are very optimistic they'll help with self-driving cars. So anyway, these networks are doing things better than any other computer science techniques that we had come up with so far. And they've also shown that the activity inside these networks has some reasonable correlation with the activity going on inside of the brain. And so that's led a number of people to think that there is a really the best way to understand what the brain is doing is by building these artificial networks and seeing how they work and studying them. And then that gives us insight into the brain. And one of the real advantages of these networks is that because we created them, we have perfect access to what is happening at every exact moment inside their networks. Whereas in the brain, we have relatively coarse methods for investigating what's happening. I mean, fMRI will summarize the activity of at least 10,000 different neurons. And for unit recordings, you can get traditionally 1, but maybe now 100 or 200 neurons. Whereas in these networks, artificial networks will have tens of thousands of neurons. So if it was in fact the case that what's happening inside these artificial networks is a reliable guide to what's happening inside the brain, then they would be tremendously valuable and give us great insights into how we're able to do things like object recognition or language production. Maybe you've heard of GPT-3, which is another. So this is the software where it can write op-eds for newspaper articles. So you just feed it enough articles, and basically most of the internet, and it can then produce very plausible seeming articles. So some people have thought that it's given this ability to do this, it must in some way resemble the way the brain produces language as well. So that would be another kind of example. So anyway, so we have this technology, which was originally, its structure, as I said, was just all these nodes are supposed to be roughly neuron-like, so it's inspired by the brain, and it can do things that are nothing else can do besides the brain. So that has led some people to think there's some kind of tight correlation between them, and we can use one to understand the other. And the point of the course is just to examine that claim as carefully as we can. So, for example, there are images that you can, to us, would be obviously not like nonsensical images, or would look like, say, a rabbit or a dog, but the network will say it's a glass of wine or it's a snake. So these are called adversarial images. That's one respect in which, even though those networks are really good, they can be fooled. And which, by the way, is one of the things that's going wrong with self-driving cars, because these networks will do a pretty good job 99% of the time, but that 1% of the stop signs you're at and accelerates because it thinks it sees, it doesn't see the stop sign, or it thinks it sees a speed up sign or something, then that's pretty bad. So anyway, so that's one of the kinds of comparisons you can make between them.
How would you use artificial intelligence to better understand the brain if we created it and it's kind of a lesser version of our brain?
Yeah, well, I don't know if it's the question is it a lesser version of our brain? So one classic study is you train it to recognize images like dogs, cats, suitcases, all this, like thousands of different categories, and it gets pretty good. And then you compare what's going on inside the network to what's going on inside the brain. And it turns out you can predict about 40% of the neural activity in the brain can be predicted on the basis of these networks. So, for example, you get this kind of, we talked earlier in vision, how you get these hierarchical representations, very simple lines and then shapes, and then you can reconstruct something like that going on in the artificial neural networks as well. So you might think it's giving us some insight into how the brain is doing what it's doing.
So we're kind of working backwards in a way.
Yeah, that's right. So you train it to do what we can do, and then you look to see if there's a correlation between, and then you assume that it's a model to how things are really done. So like an example that comes up all the time in people who study the motor cortex and and behavior is that they will then design a certain kind of artificial neural network called recurrent ones, which have connections that go backwards in the network. And they can often show that the kinds of behaviors and neural patterns they find in the motor cortex are then duplicated in these kinds of artificial networks. And so because you can study these artificial networks with much more mathematical precision than the brain, you might think that gives you real insight into how the brain is doing something. Like other examples involve like finding that I forget the name of it, the part of the brain that's largely responsible for word production. What it's fundamentally doing is predicting what word should come next. And that's the same principle that emerged out of these artificial neural networks that were trained in language production to come up, the things that are writing op-eds and completing paragraphs. And this is very cutting edge. Who knows what's going to hold up? But if that holds up, that'd be another example of how these artificial neural networks give you some insight into the principles that the brain is using, sort of the strategies the brain is using to do what it does. And then there are just other examples from decision making about this is famous task called the random dot motion task. We have to say whether the dots are moving on the whole to the left or to the right. And you can have artificial neural networks that are able to make the same decision in the same kinds of ways, which would be some reason to think that you've then captured the dynamics in the brain that the brain is using to make those kinds of decisions. So because we have imperfect access to the brain, and because these networks seem able to do similar things, the hope is that we can study them to understand better how the brain is working. And that's probably, I should say, the most optimistic case that could be made for thinking that looking at one is going to help us with the other. There's actually tremendous grounds for pessimism as well. So that the goal of the course is just to look at the evidence both ways.
So I had this crazy analogy that came to mind. I want to bring it forth and see what you think. What it sounds like to me is that you're creating something and then trying to figure out, it's kind of like guesswork with AI because we're so at the very beginning of it. So I saw this video this morning about there's a new Starbucks cake. It's a lemon cake. And this woman decided to make her own and figure out how to get this exact flavor of lemon cake and just make it herself. you kind of just make the cake and then you, well, I don't know if that analogy completely works,
No,
but
that's exactly right. So the cake is our brain.
right.
So but we don't know how it's able to do what it's doing. So we're trying to, in a way, reverse engineer it by trying to make our own.
But you can't like uncook the cake.
And cook the cake. That's right. You can't. And I like it also because you don't know what the relevant ingredients are, because it's in a way all smushed, all mixed up. So yeah, it's a lot like that. But there's another wrinkle to it, which is that when you use these artificial neural networks, what you end up with is this really large number of nodes that are all connected, and there are weights between them. But is that really the same as knowing how it's doing what it's doing? And that's, people just line up on different sides of this. So some people think yes, because you know what all the nodes are, you know what everything is doing, and that's all there is to understand it. But other people think no, it's like knowing all the financial transactions in the U.S. and claiming to understand the U.S. economy. It's just too many facts. They're too unsimple. Like, what are the underlying principles? That can be really hard to uncover.
Right.
So yeah, so that makes it especially tricky. It's kind of like this woman, instead of trying to make the lemon cake, had just like tried to randomly program a machine to make it. And then even when it makes it, she's then got to go back and figure out, well, how did the machine do that?
That's crazy. Do you think that we are going to progress in the direction where AI becomes more accepted, where philosophically, do you think we will accept AI creations as somewhat equals? As
Yeah,
like
these are the questions that terrify me. I wish I had some expertise that let me give you a reassuring, or at least a confident answer. But yeah, it's really hard to know. I mean, we've all seen movies where people fall in love with AIs that are sufficiently sophisticated. I guess I could see that possibly happening. Does that mean we'll treat them AIs as equal? Gosh, I mean, for the sake of being provocative, I could defend an answer.
Okay.
Yeah, I think eventually people tend to value other people, in part because of their usefulness. So if we get to a point when AIs are at least as useful as other human beings, and I don't see why, and have voices that sound like them, and they're able to mimic interactions that are quite human-like, it'd be hard. I mean, yeah. Well, I mean, why do we treat some animals better than others? I mean, we like cuddle our cats, and then we eat chicken. I mean, in part because cats are so easy to see as being human-like, in the way they cuddle and they purr and they interact. And chickens, they don't seem human. So anyway, that suggests that the more human-like AI can become, then the more we'll start to treat them in human-like ways. And given the nature of AI, I would think they could become at least as human-like as actual humans. So there you go. There's a provocative argument.
That is a provocative answer for sure. I want to ask you one final question, which is, if you could give advice to students right now who are studying neuroscience or cognitive science, philosophy, in that realm, what would you say?
Well, I mean, obvious bit of advice is not to let yourself become too narrow, because you then can lose track of why what you're doing is interesting or important, and you won't, as you said, you were thinking that philosophy would change the way you walked around and saw the world. Well, I think for a philosopher, learning some neuroscience can also change the way you walk around and see the world. And the more ways you can see the world, the better. I guess another piece of advice is, several times in your life, you should just do something completely different. So in my case, that was getting tenure and deciding I'm just going to go study neuroscience for a couple of years, and I'm going to see if I can start doing work that will be of interest to neuroscientists. And it's scary, but it's also tremendously exciting, and I think makes you a more interesting person. And I mean, the best scientists do this all the time. Christos Papadimitriou, this computer scientist I'm teaching with, I mean, he worked on algorithms for a long time. They worked on evolutionary theory. He's just jumped around his whole career, and I think that's a good model for people to have. I mean, the thing I'm excited about the cognitive science program for is getting people out of their disciplinary silos a bit to take courses in other areas too. So that's something I would encourage people to do regardless of what their major is.
Thank you. Yeah, I hear you, and I'm definitely inspired by you. I think it's really cool that you knew what you wanted and you made it happen. Anyway, thank you. Have a great rest of your day. Thank you for listening to this episode of Brain Banter. This episode was produced and edited by me, Lila Bear.
Research and graphic design was done by me, Melody Fang.
Research was also done by me, Anna Sophia, and our production staff includes Sam Hutchinson.
Make sure to follow us on social media. Our Instagram is @GrayMatterCU. You can also find our episodes on YouTube by searching Brain Banter by Gray Matter CU.
And if you want to request a neuroscience professor for us to interview, you can do so at our website, graymattersjournalcu.org.
You've been listening to Brain Banter by Gray Matter CU. See you guys next week!